Ok, boa tarde. Eu sugiro que começamos. Então, é um prazer anunciar o orador hoje do seminário do grupo da Álgebra e Geometria, é o José Proença, do Politécnico do Porto, e ela vai falar-nos do Lince Programming with Differential Equations. So, please, you can start.
Okay, so thank you very much, Dirk. So again, this talk will proceed in English, just make sure everyone can follow. So this work will be about Lince, which is a joint work with me, José Proença, and Renato, who is also in the audience, and I think most of you all also know. Yes, hello, Renato. So I'm working right now in Sister, which is a group that is doing real-time embedded computing systems, where you have lots of people doing more engineering work and less mathematical work, more fundamental work. And this also somehow fits part of the test set that has been doing there in the direction of modeling and analyzing real-time systems. So this also integrated in the project, in that Da Vinci project that I'm currently leading. And the goal is for you to be able to understand what Lince is capable, what's underneath, and also to understand some possible challenges that one might want to address in the future. So, first of all, Lince, what are hybrid programs in Lince? Just to give you some context. So that what you will see right now is programs a bit like the ones you can see on the left here, which look pretty much like standard C code. So something very similar to a simplified subset of C code, except at some point, besides these assignments and the while loops, you'll end up with these boxes in red. And these boxes in red is the part where time evolves, in this case for one time unit, but there'll be some differential equations being happening here. So the position, the derivative of the position with the velocity, and the derivative of the velocity will be 5 based on certain amount of values, which means that time will evolve discretely. At some points where I do some calculations, where I do multiplications, do assignments, and sometimes time will evolve continuously given by this kind of by these equations. And then you can plot it somehow like the position and velocity of a vehicle. But you'll see this in more detail. So the presence of differential equations in the middle of our standard code is the kind of things that makes our programs hybrid, and that's what distinguishes from the more traditional programs that you'll see in normal programming languages. So in Lince, we're going to look at these kind of programs and going to try to see some way of visualizing, analyzing it, or provide some insights to actually depict what it means to run these kind of programs. So this is available online. So if you go in this link, you'll see the program running these kind of things. So because it is running on the cloud and it's not really tested for many users, I'm not sure how well it will work if many people try to access it at the same time. But in any case, it's something that you can try either now or later. So what are we going to see today? Today, you're going to have these 4 different parts. We're going to start by giving a bit more emphasis on describing what we mean by hybrid programs in the context of Lince. So what can we express? We'll see then what kind of examples, what scenarios can be described using hybrid programs in aerospace or some other kind of scenarios where you might want to have hybrid programs to specify or to model that behavior. Then you're going to see better the analysis that you can find in Lince. So if you start browsing through the widgets inside our tool, what kind of things can you see? What can you learn from the programs that you have here? And finally, I'll provide a small set of possible challenges in the sense of what kind of work can be built on top of Lince to either validate its use or to justify its extension. So what can be done with the things that already are here? So by the way, this talk is interactive, so feel free to interrupt me at any moment or to post questions inside the chat as well. If I don't read them, I would ask either Dirk or Alexandre or someone else to stop me to make sure I can see the messages. So let's start by opening the hybrid programs in Lince. So I'll constantly swap to this to the demo version to show the program. So I have here on the side, I'll have here the tab open. So first, note that there's the website where this is running partially on your browser and partially on the server. So every time you do something, we'll ask the server to perform some kind of pre-calculations. So all the differential equations, all the solving will be done in the backend. The results of this solver will go back to the browser, and the browser will perform computations to know how to plot. So you'll repeat certain computations. So there's this hybrid mode between asking the cloud to do something and then process information in the browser. But because I'm not sure how stable this is, I'm running my own local version. So if you go to the source code, you can also download the source code. There's some README that tells you what you have to execute in order to start running your service, and then you just open a local HTML that will automatically use everything that's running. So you just need to make sure you have CIDMA. That's where all the calculations, all the algebraic manipulations are done automatically. So it's just delegated there. And you need some tools to be able to build and run Scala and Java. And of course, you need the internet browser to check it. So this is Lince. These are the kind of things you see. So this is the version running on ArcaTools. So the version online. Press the wrong button. I'm going to use my local version. It has small variations from the version online because it has something that I didn't upload yet. So basically, you have windows. Each of the windows you can actually minimize or maximize, and this is where you actually write your code. This is the example we saw before. So a hybrid program here is you can keep changing this and say that instead of velocity 5, they actually go for 10, will go a bit faster, and I press to recompute. Let's insist. So this will ask my local version of CIDMA to perform some calculations, and then we'll just update the turns, and you can see the graph. So let me zoom in the beginning. So this is roughly what you see here, which is plotting the behavior here. So you can see the position P. The position P starts in 0 and will either increase or decrease based on the acceleration being positive 10 or being negative -2. And then you can also plot the acceleration. So roughly, this describes how the variables P and V vary, which vary not only discretely but also in jumps. So just to give you another example, you can make everything more discrete. So in this example, you basically wait 10 units, and then after waiting, you set some value to either 0 or 1. So this gets you a very discrete behavior where from time to time it jumps between 0 and 1 at time instance 10, 20, 30, and so on. So this is one kind of program. This is just syntactic sugar for this do nothing for this amount of time. But not only that, for keyword exists, there's also a variation of that keyword, and that's the bouncing ball example is a good example of this. So if you start reading, you see here you have the velocity, the position, and some counter C. And then you repeat 4 times this behavior. And this behavior basically captures the ball falling, where the velocity has the acceleration of the gravity in this case, and the position gets the derivative of the velocity. So P here is marked as the orange color. But now we have an until. So the until, before we had the for was for specific time events. So it was triggered by time. Every time the time arrived, something would happen. In this case, this is not a time value anymore. This is now a condition where I want to stop. So this until requires, in our case, to be able to use here a number, which is the precision at which you want to to verify. So this precision makes this behavior not 100% precise. And I'm going to zoom in this point here. And I'm going to say, don't show me the velocity. And you start realizing that, and the counter also doesn't help. So you start realizing that it actually goes a bit down. That's because the precision we established to check the condition was every 0.01. So this is a kind of problem we encounter often in most of the tools that do simulation for these kind of programs. So you'll find MATLAB with Simulink and other ones where you always have to commit some kind of discrete step. But in our case, many of the scenarios that use this more fixed amount of time, you're able to actually analyze behavior without having to discretize and saying how often to check these things. So we aim here to be able to specify everything more precisely, avoiding time steps whenever possible. So this is a very small glimpse to understand that we have differential equations and that we can specify event triggers or time triggers. In this case, it's a time trigger. So also something interesting here, I'm going to press all jumps. So every time there's a jump here, it's because we just stop having something continuous and now we're performing some discrete computations. And here you can actually understand that the position and the velocity obey certain kind of equations. So you see here, pt equals the minus t square of minus t plus 13t plus 111 over 2. So this is the kind of thing that we strive for, to be able to keep manipulating algebraically these values to make sure we always have a very precise notion of where we are, because we actually store not numbers, but the calculations to get the numbers by relying on something like CIDMA to be able to give you some more algebraic calculations. So this is roughly how you use Lince. So summarizing, you saw you have some code where you have these assignments. We have some kind of loops and conditionals. These are the standard programming languages constructs. But we have these special magical things where we have differential equations, so this continuous behavior. And you have either for or until clauses to specify a time value or a condition that allows you to stop. Unfortunately, these time conditions actually require this step. Otherwise, you can survive without that step. So this is rough definition of hybrid programs in Lince. So if you go to the literature, you'll see that hybrid programs often are not really specified by a program using this programming languages kind of notation. What you'll see is quite often this notion of hybrid automata. So hybrid automata is something very popular in the context of hybrid systems, where you usually have this normal automata as you've seen, with labels and states, but you enrich the states with the same kind of differential equations that you've seen in our program, and you also enrich it with certain conditions that talked about when should these states be left or for how long they can be there. So hybrid automata is a very popular formalism where you can also have non-determinism, which is something that we don't have or we don't specify in our system. And non-determinism is something useful to have when you want to verify a big set of spaces, but in the context of simulations is something that to make life much harder to be able to analyze or model. So these are a typical model, and usually when you ask someone else to specify your system, quite often the person ends up writing somehow the state machine that specifies them. That specifies the differential equations or the continuous behavior together with the steps of your state-based machine. So let's talk a bit of application scenarios. So now you've seen roughly what kind of things you're specifying, what kind of constructs we can use. So I'm going to show you now a small 1, 2, 3 possible application scenarios where one might want to specify it using hybrid program or hybrid automata or something that has this continuous behavior. So this example is an example from SpaceX. It's a very recent launch or arrival of a spacecraft that didn't up very well. So I'll show you very quickly. It's just a few seconds. So roughly what you see here is the landing of this Starship, where you have some kind of rotation involved, and you have to manage a few thrusters to rotate, compensate, accelerate. And the goal is to make sure that by the time you land, your speed is slow enough so the spaceship will not crash. So this was around a month ago. I'm not sure exactly in which day, so it's something relatively recent. But yeah, this is what happens if the calculation is not properly done or something goes wrong. So modeling this kind of behavior is something important and still done quite often using simulation tools where not controlling precisely certain aspects or failing to analyze certain things might mean this kind of catastrophic events. So this particular example I like, and Renat was also pushing quite hard this as a motivating example, because it requires you to model not only the acceleration of the space, the vertical acceleration, but also the rotation that will affect where it's aiming at, the direction, the position. So a few more variables, not only in one dimension, but two dimensions that require you to be able to model this particular scenario. So this is the first example. Let's see if I can go to the next slide. So some of my colleagues are also at Sister modeling scenario of platoons. A platoon have a sequence of cars, quite often where the front car it drives on its own, and then you have a sequence of followers. So each car will try to find the car in front and try to mimic his direction and try to be at a certain distance from him. So you can imagine the first challenge is to know how fast the car should go. So he needs to control his speed and adapt to the car in front using certain kind of algorithm. So how quick he wants to go to the right place, he wants to go very quickly and slow down in the end. So there are several factors. So it's a typical control theory algorithm. But in this case, they also found challenges with controlling the direction. So if there's a turn, how well should he compensate? And if you program these things badly, you understand that you'll start oscillating and not finding a proper balance. So of course, the examples they're doing, they are more practical. So they're basically trying to simulate these scenarios using simulators like Gazebo or others. So using simulators that basically encode the behavior of each of them based on what they see and not based on a snapshot of the full system. So here we can, if you try, to model the precise behavior of all the system, assuming that each car can have the snapshot of the full system. So if the car on the bottom can precisely know the position, the velocity and direction of the car in front, then we can try to model what kind of algorithm can we use to try to fine tune him to make sure he's always at certain distance and following the same path. So it's another scenario that can be modeled as well using this kind of programming languages. So this is another example you'll see as well. So here I have a video of a system that simulates the flashing of fireflies. So I can put here while I speak. So these are a bunch of LED lights, and these are flashing with certain frequency to mimic the mating ritual of fireflies. So roughly, the goal I think of this project, from my understanding, is to try to attract fireflies, but also means that lots of biological events follow certain equations. In this case, we have an equation of how 2 or 3 fireflies should flash in accordance with its neighbors. So they don't flash randomly, the fireflies, but they flash according to the frequency of their neighbors to guarantee there's certain global behavior that emerges. So it's also something that can be modeled using this system. So how long you wait before you flash, and how do that you're flashing according to the flashing of your neighbors. And also in the context, in the context of the more biological world, there's also the idea of trying to model pacemakers, for example. And this is something that if you go to tutorial of Simulink, you'll see as well that they explain how to try to model the merging of signals in a pacemaker. So as you know, a pacemaker is a device that keeps collecting information about how your heart is beating. And in case of need, can inject some special, electrical signals to force or induce certain muscles to contract and to have extra heartbeats to make sure that you always have enough oxygen in your blood, that your heart is beating at the right speed. So this kind of behavior also requires the reading of continuous behavior and to somehow analyze these waves of behavior and react it. So there's also something that is could fit this kind of this behavior with continuous behavior. So there are many others that can be applied. So I'm not going to mention more, but there's this the train system, aerospace, drones. There are lots of new topics where more and more people want to validate the continuous behavior with respect to the programming inside, which is very discrete. We are constantly monitor for something and react based on that. But you want to have a faithful representation of the continuous world in order to be able to reason about this. So in this picture also have, so it's the typical control flow example where you can, in this case is for heating something, if you want to keep a certain temperature or pressure and you have some valve, how you want to make sure how much the valve should be open to adapt to the right pressure. And this is also done for containers filling with water, very similar to also to the cruise control we saw. So these kind of things are typically require a modeling of the continuous behavior of what's happening here if you want to reason about how open or close or how fast you should accelerate a certain process. So that was the first part. So now the question is, yeah, we can specify, here's a description of what my behavior that alternates between discrete and continuous steps. What can we do with it? So I think there's a range of things you can do with this. So not only to simulate the scenario as Lince is trying to do, you can also try to use it to predict what's going to happen, or you can generate actually software. So quite often, once you have the model, you use this to say, okay, I want some code for my controller. That's the one that's we actually executing here. And I'm going to use this to generate my program, or at least to guide the parameters of my program. So this is more on the side of this system engineering, and this is still something you can see applied not directly from this model, but quite often having this model in mind and after some certain experiences after experimenting with the values. On the other side, you can also try to reason about these things. So once you have the program, you can, besides trying to run it to see where it gets you, you can also try to see if you can model check properties. So if you specify a property, temporal logic or something similar, if you can verify does it hold or not. And can also do theorem proving. So the Chimera or Chimera X, these are the kind of things that really strive to look at model check and theorem proving, but introducing something that we're not looking at, which is the notion of non-determinism. The fact that we allow either behavior A or B and not necessarily impose one of them at each moment in time. So they open this Pandora box, and then they can try to verify things in system where the behavior just keeps exploding. And it's not very easy actually to grasp sometimes what's happening. On the other hand, there are tools like MATLAB and Simulink where you can generate here where you need to control in more you need to fine tune better this precision, the discretization of the steps. You need to be a bit more verbose in the model that you write here often, and quite often induces certain errors until you actually get the right system here. So these try to place what Lince does, and there are many other things you can do with hybrid programs. So let's see a bit better now what kind of other tools we can do in Lince. So we already saw roughly how to grab something like a cruise control, and now I'm going to try to illustrate a bit more this which I already showed partially of these algebraic calculations, and then a bit better feeling of the if statements and some other experimental features that you might have here. So feel free also to stop me and to ask me to try things. So things I want to show here. So this is a very simple example of composition. So here we have roughly 3 behaviors in separate. V sets to 0, then V grows at speed 1 for 2 times units, and then V grows at speed 3 for 2 more, and end up there. And if I press here all jumps, we'll highlight every single step and be able to see the equations inside. So I want to show now this more complex example, a variation of this, which is this one here. So this looks very similar, where you have a certain initial value, and then you say that a bit something more complicated. So x, the derivative of x is minus x for 40 units. And then you do the opposite. Now it's positive x. So you see here that the solution is actually e to the power of minus t. So it's an exponential equation, the solution of this differential equation, which means that after, I'll want to press here all jumps, after 40 steps, you reach a point where the where the value of x is 4.24 something to the power of minus 18. So it's a very, very small number. And once you do the opposite step, you reach the point 1. So as you can imagine, this is something that is very sensitive to perturbations. Small errors will get you the wrong value. So here, when I ask in the end, let me check that the value is exactly the value of 1, then change my program to either 2 or 3. This is extremely prone for something to go wrong. And if you try this in most scenarios, most examples, even if you program this scenario using Haskell or your favorite programming language, very likely this value, this condition will tell you false. Because after calculating these values, the precision that they use by default is not enough, and you end up approximating this to 0, or at some point the numbers are just not manageable, and they'll not get 1, but something close to 1. So this is the advantage of manipulating values using them using this precise this algebraic symbolic representation other than the actual value. So you can also ask and say, can you tell me the value at 40 at time 40? And I press to evaluate. So you'll try to recompute this again, but you'll present me this value in terms of its symbolic value. So it's actually e to the power of minus 40, which is something very easy to manipulate. And then you have the actual value that you can obtain from it. So you can also do other things like derivatives that depend on each other. So actually this has a solution which uses sines and cosines. So of course, this means that you have to solve this system of equations. And the truth is that you cannot solve, they are not known, there are no algebraic methods to solve every single solution of differential equation, but it's relatively complete. So if you look at CIDMA, they're doing a very good job to be able to get a very big class of equations you can do. More than that, we don't allow here to write any expression. So this actually has to be a linear construct over the values that you have. So we actually using not any system of differential equations, but only the ones that are linear here. So we can get interesting simulation. This is an example that if you try to use approximations and you try to use numerical approximations to calculate these values, you will end up in bad results in no time. So this kind of simulation is something very hard to get using the more traditional step-based functions where you try to compute these we try to solve the system of equations in a more numerical approach. So you see that now that we can calculate, I'll do it again. So at step 2, what can we have? You see that you can ask for each position exactly what are precise values, what are the expressions that's under the hood. I'm just going to show you one more example, which is this landing system. So this interesting example, which models here the height of the airplane, let's say a spaceship landing, the same you saw, but now vertically, though is perfectly aligned. And we define 3 loops. So we're going to say that in the beginning, when it's higher than 1,000, so more than 1 kilometer away from landing, then if the velocity is smaller than -100, then accelerate one direction, accelerate at this speed, otherwise accelerate at this speed. So it sets different acceleration values, positive or negative, and use the system of equations for the speed. So roughly it has different ways of adjusting the acceleration, with bigger jumps, with bigger accelerations go up, or small accelerations to have a stronger but less precise impulse in the beginning, and a softer and more precise in the end. So if you go to this very end and ask to see what's happening here, you see in the final step. So the blue one is the height. It will stop here at height 0.95, which is our stopping case. It's our precision of 0.05. So we can model this landing system with 3 phases where you use different acceleration values. And you can now start hiding acceleration because you don't care about the G is a constant. You also can take it out. So you can start visualizing and understanding what's happening inside. And you can even ask to show every single possible jump, and then you'll see there's a bit too much information. But then you can gossip at each moment what are the actual equations that are being used. So it gives you some insight of all these steps in the middle, and you can model things like the airplane going down at different accelerations and using different algorithms for the acceleration. And if you mess up a bit this value, what you end up is understanding that, so if the velocity is a bit higher than this, I don't remember which number can go wrong, but I'll try a bit higher speed. Very easily, this will crash. So this allows you to experiment and understanding up front which numbers it will work or not. Okay, so you can see here at instant 3, if it goes at 5,000 the speed, initially it will just crash immediately after 2 times units. So you can experiment with this and understand which values actually work or not. So I'm putting now even just double the speed. We already said that it will stop and crash. Let me hide the velocity. It will crash roughly between instant 5 and instant 8, which is when the y, the position will be negative. So this is the kind of feedback that you can get. So you show that it's important to have these if statements precise, especially if you use the equal. Typically, you end up using higher or smaller to play on the safe side. But if you're doing algebraically, then you can actually have this equal in your if conditions. And we also did this small experimentation. So I'm going to show you here in the context of the cruise control. So we experimented here with this notion of perturbations up to. So let me try putting a value 2 here, and I recalculate here. So here I got now this kind of balls, which are warning points. I'm going to focus a bit on these ones. So this basically saying that at this instance, if I perturbate my value that I'm testing, so I'm testing is it V smaller or less than 10? And by having a perturbation of 2, then you'll get me a different if condition. So this condition is not stable enough at that point with this kind of perturbation. So we can start. This is an experiment we did because it uses some more some numerical approaches to try to get to it. But this is one possible direction, which the kind of things that the tools from Simulink and others, they are particularly good in. So roughly this one of the experiments. So in this case, at this time, they actually says that you're testing something with just the tiny perturbation. Any small perturbation will make this jump change, which makes sense. So this V is exactly 10 at this point, which means instead of 10 is 10.0001, the if statement will get you a different behavior. So quite often this helps you understanding what can mess up in your system if you have small perturbations in your actual implementation. Okay, and there are also other small examples, like, so you see them. So this is the fireflies example we saw before. We have 2 fireflies. Let's just wait until it computes. Where you see here, I can drop these perturbations. So where roughly you can now see how the flashing works. So so basically this is so the evolution of the 2 fireflies that grows linearly, and at some point they are reset. So the normal behavior is grow. When it reaches 10, it becomes again to 0, which I believe they are the frequencies. The explanations is mentioned here before. But in any case, the important thing is that the conditions, they check they check the frequency of both of them in order to know if one of them should stop or not. So you can model the behavior of multiple fireflies using this approach. What I wanted to show you now is in this bouncing ball that you had here before. We have these precisions of 0.01. And you can see, for example, in this jump that I showed you before, you actually can go to 0, and it goes up to this precision that we put here. So we have certain way of saying, I want a higher precision, but this will mean sampling very small steps. So I can do, there's some kind of algorithm inside, and I'm going to show you very quickly now just the result. So if you now look carefully here, and I'm going to zoom in a lot. Now we got a much better precision here. Then let me hide again. Let's see if it's already negative. And resample. Oh, I need to hide this counter. Yeah. Okay. So what we got here is, you see that the precision is already at level of this 0.00001. So this experiment, the thing we're doing is we go with this precision first, and then for this interval, we do some kind of jump halfway, then jump halfway. So do a logarithmic search for this point. But if you look at the warning here, it says be careful. We are assuming that with this precision between 2.0 and 2.1, the value, the condition p less than 0 and v less than 0 only becomes true once. So this is yet another experience to try to get some tools, but that don't add anything to the actual core of the system. So we can do this kind of experiments, just try to make it more useful. So these are the kind of thing we have now in our tool. You're free to experiment with more examples because that's what you want. You want people to understand if it's useful for them in somehow. But now I'll go to the very final part, which is giving some possible ideas or topics of things that you might want to do and play with this tool, especially if you're a master student, you want to do some kind of project that fits here, or if you want somehow to use this in the context of your own work. So I put here 3 different challenges. The first challenge could be trying to model a concrete scenario in Lince. So we have this very limited set of experiences, as you saw, but maybe trying to model the steering in this platooning system, or the rotation in the landing of the system of this particular landing that went well, that went badly, might be an approach. So we might want to try to see, understand which scenarios will be useful to model here, something you didn't thought about before. And it would be interesting in this context as well to experiment or to understand if is there any language extension that's important. So here I'm exemplifying one. So right now we cannot really specify the behavior using a normal expression. It's something that technically is not hard to do, especially because all the machinery is there. But if someone tells me this is something very useful because I don't want to always specify this using a system of differential equations, this is something that we can also consider extending. And there might be other extensions that might be useful aligned with this. So this challenge, besides possible modeling, is justifying using the model to explain how new extensions could be useful, or even extend them themselves if you want to put your hands a bit dirty. Then it's also possible to try to provide these extensions. So this is a possible challenge. Scenarios, extensions to be able to model and specify something new. So aiming at specifying a system. Another challenge that could be interesting as well is to try to understand how these kind of programs can be modeled and how is their counterpart in the existing tools. So Chimera, for example, it has a language for specifying system which is very similar, but you have the kind of if without condition. So basically a non-deterministic choice between 2 sets of events. So in this case, you can model by saying, yeah, well, you can randomly choose between doing the first line or second line. So being able to specify this gives you extra power to express things and makes this system quite often very noisy. You want to specify a more random amount of things. But in any case, they have a language that is a superset of this. So it could be interesting to grab this and saying, let's generate the exact language, the exact syntax ready to be fed into Chimera, or to write models under certain assumptions and parameterization to make sure we can produce a similar model to be simulated in Simulink. And once this is done, then the question that arrives is, what can you do here? So you can either customize, you might need to customize parameters, you might have some kind of property in mind that you want to prove. So can you really automatize somehow this process, or do you want to provide extra information inside Lince or next to Lince to make sure we can control this use of external tools in a smarter way? So in this case, you might to specify a property. That's something you want to also transform into a property in Chimera that takes into account the same kind of coding you do there. So this could be something also interesting, which means understanding one of these. So if you're more from mathematical side, you probably want to experiment with something more fundamental as Chimera. If you're from a more system side, you might want to experiment with something as MATLAB, and seeing what kind of extra information might be useful to provide as well. Finally, let me see if I have a 4. Well, so there's a third challenge. I'm not sure I have a 4. The fourth challenge, let me just turn off my notifications. So another challenge is trying to now experiment with logics, not having in mind the tool that we want to support, but having in mind what you want to express and want to specify. So right here, I put examples of logics that are often used when you do runtime verification, which are logics that quite often use some kind of a metric or value that's accumulated over time. So what kind of logic would fit well? The kind of programs that we have here, which are deterministic programs that reflect basically a trace and execution of your system. And you might want to verify things like, is it true that velocity will never get higher than 10 for more than 2 time units? So this kind of property, when specified, requires a fine-tuned temporal logic, and there are different logics that you can use for here. So one of my colleagues worked recently in the kind of metric temporal logic that involves durations and some kind of extra values to be able to model it. But there is more work in this direction. So it might be interesting to experiment with semantics of logics, take into account this system as our guiding system, as our cryptic structure that we're using it underneath, and understanding what kind of things will be more useful and motivating with scenarios that we have here. So this could be something that would fit very well, and there are different languages that one might experiment to try to model this kind of properties. And yeah, and that was my third challenge. Of course, there are variations of this, and there are more things you can do. So just to quickly wrap up, so I present you what hybrid programs are in the context of Lince. Then I show you some scenarios of where you might want to use these hybrid programs to specify scenarios in the physical world. I show you a bit the kind of things you can press inside Lince. So something I didn't tell you, for example, if I'm going here, is that these buttons are very efficient. So you can press this many times to refresh, to present all jumps. So these are computations in the browser. If you press this refresh or this refresh here, that requires asking your big algebraic computer to calculate all the equations for you again. So there's this division of tasks between calculating these intermediate values, this interpolating is something simpler, getting these systems to solve, that's the heavy part. And finally, I have these ideas for challenge or future work of something that can be used to try to produce some extra scientific content or experimentation in the context of Lince. So that's it. My website also has more information about things I'm doing, my email, so feel free to reach me if you want as well.